Hello. Now we'll do the adiabatic process. In case of adiabatic process, the equation is dq is 0. So, in case of adiabatic process, there is no heat transfer happening between the system and surrounding and system. There is no heat transfer which happens there. So, this is the equation dq is 0 in case of adiabatic process. But as you know that we want the equation in terms of pressure, volume and temperature. We like them. We tend to go by those equations. So this equation we want to modify and we want to convert this equation in terms of pressure and volume and temperature. It's preferably in terms of pressure and volume. Okay, so we'll do that. So dq is 0, that's our equation for adiabatic process. What we will do, we'll go by the first law of thermodynamics. If you go by first law of thermodynamics, we'll have dq is du plus dw. So this du and dw, if you see, the du, this is my equation 1. The value of du is ncv dt. Whatever kind of process you are talking about, the change in internal energy, if it is idle gas and if the system is closed, the change in internal energy of the system is equals to ncv dt. And since the system is closed here, and then in that case the work done can be done as pdv. So this is my first law of thermodynamics, and this is the value of dq in case of adiabatic process, and these two are the values for the closed system. We'll put all these values in the first law. If you put the value, from equation 1, if you put all these values in equation 1, we'll have 0, since dq is 0 there, is equals to ncv dt plus p dv. So this becomes our first law equation when we put the values. So let's take this here. So p dv will become minus of ncv dt. So this is the modified first law, modified form of first law for adiabatic process. This is my second equation. Now here you can see I'm having three variables, p, v and t, and so it will not be easy for me, it will not be possible for me to integrate. So what I will do, I have to replace one of the variable. So for that I'll use the ideal gas equation. So if you use ideal gas equation, which is pv is equals to nRT, this is my ideal gas equation. If I use this equation and if I replace the value of p into equation 2, so from equation 2 and 3, let's replace the value. So we'll have nRT dv upon v is equals to minus of ncv dt. Here we can cancel this n and n. Along with that, if we separate the variables, upon separating the variables, we'll have r dv upon v is equals to minus of cv dt upon t. We'll take this there. So now we have only two variables in our equation, differential equation. We will integrate. So if we integrate, we'll have r dv upon v is equals to minus of cv dt upon t. Since cv and r are constant, I've taken them out of the integration sign. We'll integrate them, this equation. So if I integrate this, we'll have r times of ln v is equals to minus of cv ln t plus some constant. There will be, I have integrated it indefinitely. Okay. Or since if anything is outside of the r, we can take it inside the ln and we'll put it as the power. So it will be ln v to the power r. Here also minus will become plus if I take it on this side, ln t to the power cv, and that is equals to constant. Or we can say ln v to the power r multiplied with t to the power cv is equals to constant. We have taken that side, ln a plus ln b we have applied. Let's take the anti-log. Upon taking the anti-log, if we take the anti-log, we'll have v to the power r t to the power cv. Then here we'll have e to the power constant, and e to the power constant will be one more constant, something different. It will be a constant. So now we have an equation which we derived from this in terms of v and t. Okay, so v to the power r and t to the power cv is a constant, but we do want the equation in terms of p and v. And if we want to get that equation, we have to replace this t. So we have this equation, if you see. We'll have v to the power r into, in place of t we can write pv upon nr to the power cv is equals to constant. Let's open it. It will be p to the power cv, v to the power cv, and v to the power r is equals to, and you see this n and r which are already constant once you have the closed system, and cv is also constant, so these values will go there and we'll have some different constant. Let's combine these. We'll have p to the power cv, v to the power cv plus r is equals to constant. So powers get add up. So from Myers relationship, if we say, from Myers formula, cv plus r is cp. That's your Myers relationship. So we'll have the equation which will be p to the power cv, v to the power cp is equals to constant. If on both sides we'll take the root in terms of cv, so we'll have p to the power cv upon cv, v to the power cp upon cv is equals to constant to the power 1 upon cv, which is again constant. So we have, now we have an equation in terms of p and v. So what we do, we replace this cp upon cv value by a constant gamma. This gamma is defined as adiabatic constant. So this is our adiabatic constant. Adiabatic constant. This value is defined for the gas, what kind of gas you are using. So this equation will get converted into p v to the power gamma is equals to constant, where gamma is cp upon cv. If we replace the value of cp there, it is f by 2 plus 1 times of r divided by f by 2 times of r, which will become gamma is equals to 1 plus 2 by f. So from degree of freedom we can calculate gamma, and this gamma is there. This is your equation of adiabatic process in terms of P, pressure and volume. Okay. So now one more time we'll go for it. So adiabatic process is defined as the process where there is no heat transfer happening between the system and surrounding. So dq is 0. We wanted to convert this equation into this format of equation in terms of P and V. For that, we started solving it first using the first law of thermodynamics. We solved it and we converted it into this format. PV is equals to minus of NCV dt. Okay. Then we integrated that by replacing the variable and we got this equation in terms of volume and temperature after doing the integration and using the properties of log. Then since we want the equation in terms of P and V, this was the equation in terms of V and T, we replaced the value of T from ideal gas equation. And after replacing, we got this form of equation. Cp upon Cv, we define one more constant as an adiabatic constant. So our equation gets modified in terms of Pv to the power gamma is equals to constant, where the gamma upon simplification is related to the degree of freedom. So the gamma value will be defined for the gas, whether you are having the monatomic gas or diatomic gas or polyatomic gas, the gamma will be defined corresponding to that. And if you write the value of gamma, it will be 1.67 for monatomic, it will be 1.4 for diatomic, and it will be 1.33 for polyatomic gases. If it is a combination, we can calculate it by taking just the average in terms of proportion. Okay, thank you.